Let me introduce our speaker today. We have Dr. Christian O'Reilly, who received his bachelor's degree in electrical engineering and his master's degrees in biomedical engineering, also the Ph.D. in biomedical engineering in 2012, all from Polytechnique Montreal. He was a postdoc fellow at McGill from 2012 to 2015 on 2 different centers, doing research on sleep, I believe, mostly. And he also worked, second semester, worked on EEG sleep transients. He also worked at EPFL from 2015 to 2018 on modeling the thalamocortical root, and at McGill on brain connectivity from 2020 to 2021. And since 2021, we are fortunate to have him as an assistant professor in our department. I'm excited for this talk. Thank you again for agreeing to give a talk. I'm going to sit there and enjoy it. Thanks.
All right. Thank you, Ramtin, for the invitation. I'm really happy to have the occasion to give this talk because that's a topic that is really of interest to me. It's something that I really enjoy doing, doing some data wrangling. I put neuroscience, this title, in parentheses because like 80 to 90% of that talk is about how to get data and how to analyze them and how to put them in proper format. So there's a little portion that is specific. I take a use case with EEG recordings, but people that are not working with neuroscience data in specific will find that most of this talk is still useful to them. Another reason why I'm happy to have the occasion to give that talk is, so when Ramtin asked me if I wanted to participate in this series of seminar, I thought that it was a good opportunity for me to make a pitch for my class in spring. So that's basically the topic of my class in spring. Of course, it's a much more succinct overview of the topic. All right, so I'll start by telling you why I love Python so much, and then I'll cover different libraries that are all playing well together, but allows you to do different things with your data. I've been probably generous in the number of slides, so depending on the clock, maybe I'll skip the last few ones, but the slides are available online, so and you can always reach out to me if you have questions or if you want to know more about this topic. And of course, you can attend my class in spring if you want. Okay, so so first, that's my disclaimer. Is I'm not, and I try to write it in a millennial dialect here to connect with my audience, let's say. So that's my disclosure. I love Python and I love neuroscience, and that's kind of the mix of the two. So that's why I'm passionate about the content in that talk. And so I will have a bit of a biased view, but it's kind of voluntarily. I will try to sell you why Python is great, but you can also do analysis in Matlab and other languages, but I'll try to show you why Python has some very interesting things to propose for this kind of work. So that was the situation for me personally 15 years ago. So I was doing a lot of programming in C++. I was doing programming in Matlab, programming in R for different reasons. So when I wanted to have something that was more kind of industrial grade that I can have like a commercial product, I was thinking C++, and then I could do like good graphical user interface and optimized code and very fast execution. And when I wanted to do fast prototyping, then I was going more towards Matlab, and if it was statistically involved material, then I was going to R, but these were more, I would say, research-grade software. I mean, obviously, we hope to have no bug and all, but it's not necessarily something that you say, okay, I'm ready to sell that, and it's like, you know, highly tested, and like you can send it to Mars, you know. So these different these two extremes have, like, on the C++ side, you have more industrial grade. On Matlab, it's more research grade. On Matlab, what I liked a lot is that it was fast prototyping, so I could get a solution and answer to my question really fast, whereas in C++, I had fast execution, and code readability was more on the side of Matlab, but code elegance was a bit more on the side of C++ because it has this nice object structure with polymorphism and all these nice structure of object-oriented programming. So now this is the situation for me nowadays, that now I do everything in Python. And the reason why I do that is that there's quite a few things that I like about Python. First, it has this, so you can do fast prototyping, but you can also have a more robust, more closer to an industrial grade solution. The first reason is because it has proper DevOps. So it doesn't mean that you cannot get your code, your Matlab code, but it's much more in the spirit of Python developer, Python package to do their programming as a Git repo and have continuous development. And you have a solid testing infrastructure to do, for example, test-driven development, which you don't have a lot in more Matlab environment. Python package development normally is really in a free and open spirit. If you have like something that is more C++, more industrial, it's something. Sometimes it's more like a more industrial and proprietary kind of spirit, which is nice if you work in that context. But if you want to work more in the context of open science and open source, Python is great for that because it's really part of the spirit, if you want. You can enforce also your programming style with this PEP8, which describes how the style of your programming should be. You don't have to, but you can if you want. There's this Flake package, for example, that will check if you are compliant with the PEP8, and you can generally check the box on your IDE to automatically validate that your code is PEP8 compliant. You also have very good support to generate documentation automatically from your package. So this Sphinx package, for example, is a bit the equivalent of Doxygen that was there around in C++. I don't know what people use nowadays, but it's somewhat the equivalent. So that's for the kind of robustness industrial grade if you are really doing a package. In my case, I don't work a lot with packages. I do more analysis. And what I really want to have is fast prototyping. So the high level of abstraction of the code helps with that. You can, so normally it's an interpreted language, Python, right? So normally it comes with a slow speed. And yes, it's slower than really optimized C++ code, but there's many ways to compensate that and get speed that are quite satisfying. For example, the NumPy universal function, I'll discuss them a bit later. Cython that allows you to, Cython is kind of a superset of the Python language, which allows you to give some instruction on how you would want to generate machine code out of your Python code so that you can have a compiled version. You have CUDA that allows you to run things on GPU, NumPy, which is a just-in-time compiler that uses LLVM under the hood. There's a great data science stack. So for scientific programming, it's really like a really strong language, a strong option. You have Jupyter notebooks. So some people hate Jupyter notebooks. Some people love them. I like them for some reason, for some application. I don't like them for some other application. If you try to develop scripts or packages in Jupyter notebooks, you won't like it. It's not a proper IDE. That you should do in the proper IDE with a proper debugger and project, like a software that manage the whole projects, right? Whereas Jupyter Notebooks, it's more for me about doing analysis. So you have a flow of things that you want to test, generate intermediary results. Based on these results, test some other things, and you have this full trace of your. Basically, it's not. There's a reason why they call it Jupyter Notebooks, right? It's because the idea is to have this kind of a lab book of your analysis. So the package are also generally, there's good interoperability. They collaborate well together, and that I'll come back on it. So you can optimize Python code. What I wrote there is not specific to Python. There's many saying about optimization. One is don't do it yet, measure twice, optimize once. So basically, you don't start by systematically optimizing your code. You write a code that is readable, that will be easier to develop. And when you reach problems, it takes too long to execute, then you profile your code and you find the specific bottleneck. And these specific bottleneck, you'll make sure to understand what is happening there, and you'll try to optimize these only. And with that, you'll optimize like 90% of the overall optimization that you can get with small changes that will not make your code unreadable. So although Python can be slower with good profiling of your code and adequate optimization in some bottlenecks, you can generally get a 10-time improvement in your execution. Python is a team player, so it works well as a glue language. It connects well with the compiled software that's been marketed really as a glue language from its onset. With respect to code readability, there's many advantages. So they come with limitations, but you don't have to work. So you should not work with numerical indices. If you do, it's because you have like still your C++ habits or your Matlab habits, and it's not the way to write a nice Python code. You don't have to work with pointers, which is a huge relief for C++ programmer. Well, in some cases you miss them, but not that often. You don't have to deal with data types again. Sometimes you miss them, but for the most largest part, it makes your work much faster. And now they actually, the end yet there is to say that now they added, you can now give type ints to say that function, that argument should be that type. It will not be enforced, it will not crash if the improper type is passed, but your IDE typically will report that you have a problem there because you try to pass a type that is not a subtype of that specific type that you say in your ints. So there's some support there to help you manage the types. Compilation headaches, you don't have much compilation to do, so that's also a big relief. So you can still have some headaches if you want to use packages that have been coded in Python for efficiency, and then you have problems sometimes compiling it, but it's much less. It's a much less big problem than in C++ work, for example. It's object-oriented, so that's a nice thing. And the small face next to dictionaries is how I feel about them. When I think about them, I look like that. It's so much more enjoyable to work with dictionaries in Python that, for example, in Matlab, you don't have this concept of dictionaries. And if you do a lot of Python code and you go back to Matlab, you miss them dearly. So that's a little bit of why I like so much Python for my kind of work specifically. So there's different equivalents with other language. So package that has been proposed to kind of cover some aspect from other language. So you have the NumPy and NumPy and SciPy that cover well the kind of thing that you would do in Matlab. So when I was working, as I was saying, 15 years ago with Matlab, I had like this relatively big project that I wanted to convert in Python, and I found a website that was giving like all the equivalents, and over the weekend I could just like map my whole code from Matlab to Python, basically with NumPy for the kind of matrix operation and for SciPy for more algorithms if you want, and Matplotlib for the plotting functions of Matlab, for example. There's also Seaborn for plotting, which I'll discuss shortly, which gives a like much easier way to do very nice plots. Plotly, which is for interactive plots. It's not Python specific, but sometimes it can be useful. You have Pandas and stats model that cover well the concept, for example, of data frame and different linear regressions and stuff like that. And MNE-Python, in my case, to cover these EG typical software. So with respect to speed, I just took a few graphs that I found there. So you have, for example, here, so the slower curve here is pure Python, but you can optimize it in different ways. So you have, for example, the purple curve there that is next to the last, to the bottom one. Which will be faster than an optimized C++ code, for example, or a naive, so not optimized, but with this O2 flag C++ code. If you do optimize your code, you do your best to have everything as optimized as you can, and you compile it in the most optimal way, yes, you still get a bit, more or less one order of magnitude of higher speed in C++. So of course, if you need to have a small footprint and you need a very efficient code that you'll run 1,000,000 times, you might want to do this bottleneck in C++. But for your daily analysis where you want quickly results and well, whether or not it takes whether it takes 1 second or 1.5 seconds, it doesn't really change your life. You're much better with Python code. The other graph are just making the same arguments. So nothing is perfect. Python also has its quirks. One of this is these bindings that have been developed, for example, in C++, and you just have a wrapper around them. Often you have problems with the installation of the dependencies, and that can cause some headache. Also, these packages that have been just wrapped around, you don't have a lot of code introspection. And just as a side note on code introspection, that's also something that I like a lot with Python. You can easily list, okay, that's the member of this class, and you can check, okay, where is my code? And you can go look at the code. If you are working in notebooks, you can just directly ask for whatever function you find with this dir keyword. You can check, okay, what is the documentation for that function? And if it's not clear enough, you can also still with NumPy, adding these 2 interrogation marks that get directly the source code there. Often what I would do if I need to debug in that, I would just copy the code of that function locally in my notebook, and then I would tweak it as I want, and then make sure that I understand how it works, and either create a separate function in a separate file, or maybe I'll just solve my problem on my own side and continue using the default implementation if you want. So it's very flexible for that. Okay, NumPy. So NumPy is really the backbone of scientific computing. It gives you this kind of Matlab functionality of having matrices and vectors that you can use in mathematical operation. So the native Python lists are very flexible. They are very useful in many cases, but they tend to be very slow. And the reason for that is that it comes from their flexibility. Each element of the list can be whatever type of object you want. Anyway, in Python, everything is an object. There's no basic type, so it's just a list of objects of whatever type. So there's all sort of type checking validation that needs to be done under the hood, so that slows down a lot operation on large arrays. So to get around that, NumPy implemented what they call universal functions. So the idea is to implement, so these universal functions, they will work on arrays, and these arrays will have a single type. So you don't have any more to do type validation and things like that on each elements of your arrays. You know that this array is that type, and you can process it at once. It also uses contiguous memory blocks, so that also for operations, it speed up a lot operations on these structure with respect to Python lists, which can be all over the place in your memory. So just using these NumPy arrays instead of Python lists, you can obtain, for example, here a speed up of 150 times. So yeah, Python is slow, but there's ways to do things that you don't have to suffer this the slow aspect of Python that much. Also, you want to avoid loop. If you can vectorize your code, it's better because you'll use to full extent this capability of NumPy. It used to be the same in Matlab. That's where I learned actually to vectorize my code. It was making a huge difference. I read that it's not so much the case anymore since version R13, where they use a just-in-time compiler, and looks like now loops are not that evil anymore. By the way, it's also true for Pandas. You will want to avoid looping your rows to get to have good speed. You will want to do operation directly on like on the whole columns, for example. And you can also have a good speed improvement, about 20 times, by using this aggregation function. For example, here you have the basic min function on the list of number versus if you convert this array, this list in a NumPy array, and you use the NumPy min function, you gain you increase your speed by a factor of 20 times. So you want to take benefit of these functionalities. Another thing that came with NumPy is this concept of broadcasting, which is a very useful feature, but can be sometimes a bit not straightforward for novice because you start adding vectors, and the size of your arrays change, and you don't necessarily get what is happening. Actually, the rule of broadcasting are described here. They are not that complicated. It's just if you have, for example, so the third case is a good example. You have here an array that is size 3 per 1, and this one is size 3. So you have 2 dimensions and 1 dimension. So the first rule will tell you will left pad it with 1. So you'll have 3, 1 and 1, 3, and then you'll broadcast both arrays in as explained in 2a here. So they will become both 3 by 3 or n per m, and you'll just duplicate them in the along the dimension that was 1, and that become this other dimension. Yeah.
You mentioned that contiguous memory allocation is needed.
Yeah.
Doesn't that make it better? No, I still
If that makes it slow,
yeah.
The broadcasting?
Yeah, not broadcasting. I'm talking three phases.
No, the fact that it's contiguous in memory helps NumPy to make things faster.
For row-wise, for column-wise. For row-wise, contiguous is good.
Yeah, so this whole block will be contiguous in memory.
Okay.
So the NumPy keeps in memory that the shape and map it. I'm not sure how it's done under the hood, but this whole array will be a contiguous block of memory. The downside is more on the memory side. If you don't have that side, if you need to have a huge array and you don't have this contiguous block, Yes?
Just a comment on Mr. Ravindran's point. The problem of optimal selection of shapes of matrices has been studied for a long time. Usually, the traditional approaches to dynamic programming algorithms to decide what is the best way to arrange a number of the matrices that are involved in various operations. And there is, I suspect, behind the hood, below the hood, under the hood, I guess, NumPy does something like that.
Yeah, maybe I don't know exactly how it's implemented. I know that like Python, for example, has they optimize for the list. For example, the fact that the list can increase in size dynamically. They have this algorithm that allows them not to increase the size at every operation. They will systematically take a relatively like a block that is proportional to the size of the array, but that is not just like you need to add one element. They will not just attribute one element. They'll add a good block so that you can add, and they don't have to do these reassignment too often. NumPy arrays are fixed. By contrast, NumPy arrays are fixed in dimension. If you want to increase the size, you'll have to create to copy it in memory in a new array of a different size, so that it may from the start it attribute this block and in memory, and that's it. So that's sometimes it can be a bit annoying. You would like to do operation in place, and it's always giving a copy of the object. So you have to learn how to work with that. The counterpoint of that is that the fact that it always returns the object. It's nice for chaining operations, but maybe not. It's maybe not so efficient if you have very huge matrix that you constantly change size, for example. Other interesting functionalities of NumPy is that it has a very flexible indexing strategy. So there's a few indexing strategies that are listed here. So you have the normal indexing, as you would have in Matlab, where you just give the index number called index. You get the whatever is at that position. You're going to have fancy indexing, where you pass a list of indices there. In that case, the index, so starting indexing at 0, so the value at the second position, third position, and the last position of the array. You can use slicing, so from the second, because it's indexed from 0, to the fourth, so you never include the last number in Python slicing like that, so it would be up to in this the index 2. You can also use masking, so just a list of true and false to say which one you want, and you can mix and match these approaches. So for example, here I have a 2-dimensional array, and here you have fancy indexing, and here you have slicing. So you can also use that to assign values in an array. So that's a very flexible scheme. For example, again, if you compare with Matlab indexing, which is a bit more rigid. So you just have to be a bit careful, because there's some different, like when novices get into Python, and when you work with lists, the operation on lists and arrays will not act the same way. If you add 2 lists, it just concatenates the list. If you had 2 arrays, it sums the elements of the arrays. So, I mean, that may seem trivial if you have been working with NumPy for a while, but it always ends up tripping you at some point, because sometimes you convert from list to array to list because they have different properties. And if you are not careful, you think you're operating on an array, you're operating on a list, and then, oh, the size of my array is not what I thought. Yeah, but it's actually a list. So that happens often, even when you are a senior programmer. And even like the function, like, so actually that part is directly due to what we were discussing. Unless you can happen a number, because it can grow at runtime. You cannot do it in NumPy, so it's a bit more cumbersome. You have to take your different iterables and concatenate them explicitly to create a new array. So it's a bit more cumbersome, but it's the downside of having this improved efficiency at computation at running time. All right, MNE-Python. So MNE-Python is what allow you to, it's really the mothership of software for EEG in Python. And there's not many smaller ship. it's really, if you want to do EEG, it's in MNE-Python. Here I just show an example where I create, I just create a NumPy array with random numbers. Here I just make sure that they have this 1/f distribution. So there's the spectrum of EEG has this 1/f relationship where the amplitude decrease with the inverse of the frequency, right? So I just make an array like that has this property, and MNE-Python allows me to convert it as kind of an EEG recording. And then I can use the plotting function, so that would be my surrogate EEG there, which kind of look like EEG. The only difference here is that the channels are not so well correlated with one another. But so I wanted to show that just to show you that these library works well together. You can like do all things like a really NumPy stuff, like work with your data, change whatever you want, and then you can put it to MNE and use it, and it will go directly if you want. But for the rest of the example, I'll use actually through EEG that comes from an open access database. So first line, I load that file. Second line, I just set a montage, so the montage of electrode, right, that describe where the electrodes are. So when I do that, this last function return my raw object, which is my recording, and the notebook would just display its property automatically like it's shown there. And then you have different functions, for example, for plotting sensors. And so that's just the distribution of the sensors, giving the montage. These are the different power spectrum density at the different position and the head. So that's very convenient. You can look your data fairly easily. Now, what you would want to do typically in EEG is you want to, well, most EEG recording will be epoched in their structure. So you have some paradigm where you give a stimuli or something like that, a stimulus, repeated, and you want to epoch your data by window according to that stimulus. So that's the epoching part. That's arguably not the most user-friendly part of the, yeah, question? No, just stretching. That's not the most user-friendly part of MNE to create this event structure, but once you have it, you can generate this epoch structure where you can still, you have still different functionality, for example, to show, so that shows the signals at the different channels on the head, and that's just, imagine you have a 2-second window that you average across your epochs, and you can see the distribution of your scalp at different time during that time window, during this epoch. And that's really just a parenthesis. MNE's, like the oldest version that I can find on GitHub date back from 2014, and they are the next one will be the 1.0. So I guess there will be a big celebration in MNE team probably 6 months down the line. But it's a very, oh yeah, the other thing that I wanted to show here is that it's a very stable, strong, active, dynamic project. You can see there's like 256 collaborators, and there's over 1,000 packages that depend on MNE. So it's a very well developed software, and I actually contributed to that software, not big contributions, but a little bit. So I'm familiar with their process of adding code to it. And they, again, when I was talking about DevOps, they have really good, strong DevOps. So of course, there's always bugs, but they very have like this strong process, which contrasts to some more Matlab project where you don't have this such a good DevOps structure. Pandas. So Pandas gives you this data frame functionality that those of you who work with R will be familiar with. Those who didn't work with R, you can think just of a spreadsheet. It's basically an object that captures a spreadsheet like in Excel. And Pandas allows you to do different things. So if you work with the data to do data analysis, Pandas, for example, allows you to go from the wide format. So for example, here having all the columns as all your channels to a long format where you have a column that tells the channel and a column that tells you the value of, in that case, the EG. So that you can do easily with Pandas. And you can do things, for example, here I do a group by, so you can, for example, say, okay, I want to average across some of these dimensions. So here I want to have, so in that one I had, let me just check back so I had, so condition, epochs, channel, and time. So here I keep just time and channel. So I average across the other condition for each point in time. So for example, if I had many subjects, I would average across subject, and I would have one value per time and channel. And you can, when you do that, you can apply different aggregation functions. So for example, here I use the NumPy mean function, but you can also create your own. So trim is that it's not supposed to be thin, it's supposed to be trim. So it's a trim mean. So it's a mean that you cut at the 10 percentile, 5th percentile, I think, in the 95th percentile to remove 10% of your data. So you can apply that to, for example, to EG and an absolute value of EG, and it will create you this table. So Pandas is very flexible, so you can have these multi-level indexes, both in the column and the array. That can become, that is a very powerful mechanism to have, if you have kind of a hierarchical structure. When you work in data frame, it's a flat structure, right? So sometimes you miss your data really have some kind of hierarchical structure, and you don't want to go like full relational database. So you can have these hierarchical indexes in your data frame structure. Here I'm just showing that, yeah, they are indeed both the rows and the columns, they are indeed multi-level index, and you can see the different value. So you can easily say, okay, I have my data frame, I'll take the EG, and for my index, I'll just, let me just go back. Oh, you have it here. So you have two levels, right? One is the time and the other is the channel. And you can say, okay, the index 1, so it's actually the second level. The second level, so my channel, I want to select the group AF3. And then I get the data just for this specific group. And then I could pass it to Matlab and directly plot my signals here. So it's one thing that I liked a lot about Python to do this kind of analysis is that it flows relatively easily. Generally, I can get from, if there's not a lot of pre-processing that is complicated just because of the nature of the data, if it's just doing data analysis, I can, or if I'm giving clean data, I can go from like reading the CSV file to generating all sorts of figures very fast. And that is, well, we are all busy, we all have to publish or perish, so we all want to get the result quickly. And Python is very, I think it's very strong, has very strong pipeline to get this done quickly. I'm slightly running out of time. I'll just show here. Seaborn is interesting because again, if MNE-Python is the mothership for EEG software in Python, Matlab is the mothership for plotting. Seaborn is kind of the, I don't know what would be the analogy, but kind of a nice wrapping over the mothership. It makes making nice figures very easy. So generally like 1 line, 2 lines, and it's built on top also of Pandas. All these libraries are cooperative; they work well together. You can, for example, so this was, I have a data frame there, this long DF data frame. I'll just pass to Seaborn, and I'll just say to Seaborn, okay, in X take the column time, in Y takes the column EG, and as you use the channels, so it will make different color for different channels. And in the data, I just select 4 channels so that I don't have 68 channels overlaid there. And it's basically that. It's one-liner, and I have, well, it's not a nice picture, this one, just because it's not a nice way to, it's not a signal that you would want to plot that way, but well, just to illustrate this line plot. So these line plots show you the 95% confidence interval also, which is kind of a nice addition. It do bootstrap estimate of the 95% interval confidence under the hood, so you don't have to worry about doing it yourself. You have all sorts of other functions that are available, and actually Seaborn has a nice gallery of examples. So when you want ideas on how, like, to have very nice figures for your publication, ideas how you can display your data, you can consult this library, and it has very nice representation that you can achieve easily. So I'll jump now to the conclusion and skip the other libraries, but if you are interested, you can always look at the slides. They are available, as I said. But in summary, I think to do scientific programming, so I work mostly in neuroscience, but that can be applied to any kind of scientific programming, data wrangling. I think Python has a strong set of packages that allows you to do a very high level code. It's a highly expressive language. It has a strong and active community, so it's easy to have feedback, to have answer to your questions. There's constantly new packages. So sometimes there's some areas, oh, I missed that. It's like well developed in Matlab. It's not, I don't have a strong equivalent in Python. Quite often, like 6 months later, there's a package that is proposed, and yeah, at the beginning it will be a bit rough, but I've seen, like, over the last 10 years, many areas that was not well developed are now really strongly supported. It's rooted in an open source spirit, so that's if you like this kind of spirit, it's nice. Generally, the packages are very cooperative, so I skip a few ones, but there's all sort of functionality that they are all built on the other packages, so you can convert from one to the other easily, move from one to the other easily. It's not as if it's different projects and you have to manually kind of massage your, like, output your data from one package, message them to put them in the other package. Generally, you will have directly export from one package to the other so that it flows easily. There's some features that you may still miss in Python. So for example, for a long time, I missed mixed effect model. Like if you have a strongly structured, you want to do linear regression with like hierarchical structure, It used to be not well supported. Now it's supported. Last time I checked, there was quite a few limitations, but I think they have been mostly addressed. But the thing is that the researcher, the faculty that developed these approaches, they release them in R. So of course the R package is always in advance, right? It takes a bit of time for Python to catch up and integrate these features as the developer feel the need for these features. Specifically in neuroimaging, there's a lot of software that has been developed in Matlab, so there are some approaches that you will just not have directly in Python. Although you can easily communicate so you can load Matlab arrays, for example, directly in Python, work with them, export them, and you can more or less integrate the two language. Even in Jupyter Notebooks, you can. There's this magic comment that you can say at the beginning of the cell, this is a Matlab cell, and you run it, and then the next cell can be Python. So you can do some part of your code in Matlab, generate an output, continue in the next cell using the Matlab output in your Python code. So there's a way to integrate this when you don't have like a specific domain software exists in Matlab or a different software. You can most of the time integrate it with Python, which, as I was saying, acts well as a glue between different language. Also, again, more specifically to neuroscience, because that's the subfield that I know most. If you do, for example, MRI data, it's still lots of bash script, like generation of bash script built on one another. It's, for someone like me, it's a complete nightmare when you're used working in Python and you have to decode like pages of bash script. But that's the status. So generally, there have been the Python community started to build kind of wrapper around them with these kind of pipeline that you can pipe different script command line tools through Python coding, but it always feels that's kind of clunky because that's not been developed. It has not been developed in Python from the start. It's kind of just a wrapper around something else, so it's always a bit limited. But Python is constantly closing the gap. As I say, if there's something missing now, maybe in 1 year, it will not be that much. It's fast evolving. There's my email. You can always feel free to reach out. You can ask me like questions, if you have feedback, if you want to know more about some aspect that I discussed. That's also the URL for the slides if you want to have access to the slide, or you drop me an email and I can send you the link if it's too complicated to write the link there.
Yeah. Do you guys have any questions here?
Yes, Python gives you more flexibility, but don't you think that this flexibility comes the price of code? Let's explain what I mean. In C++, if you want elements of array, you say A square brackets n, or whatever number, or I. But in Python, you have this slicing, you have proposed indexing, you have nested indexing. Don't you think that this flexibility comes with price for making code not as readable as you might want?
I don't think so. I mean, maybe as you first arrive in Python and you are not familiar with this mechanism, but as you get familiar with them, what happens is that you will be able to do something very easily and very succinctly and in a very intuitive way with one of these indexing approach, for example, that you would have to do something like very contorted, for example, like generate a vector of indices and then reuse them, which in the end makes your, that's my opinion at least, your C++ code more hard to design, also hard to understand for someone that come from outside into your code. What I miss from the C++ code is this nice division between the header and the source code, and this .h.cpp, and also the structuring of the class. It's kind of, there's a nice structure to C++. But it's a bit, it's heavier to develop. Like what I can code in C++, I can code like so much faster.
It's just one person who really likes C++ talks to one person who really likes Python.
I used to love C++. It was my language for years. I started doing C++ in 2000, and I stopped doing C++. So it was my main language when I was at well, with the kind of technical college, if you want. I did like 3 years using C++, and I was doing everything in C++. And even when I continued at engineering school, that was my main language. But when I started working in Python, that's like just the thing. Sorry?
Python is immediately used for it. It is such a good language.
Yeah.
Easy language, no pointers.
Yeah. Yeah.
I like pointers. I prefer pointers. Don't tell me no pointers.
So C++ has its place, right? If you do like embedded software, again, like you are very careful about the footprint of your language, and you want to optimize it, like everything, and it's like real-time processing. You need like you need to have like control on everything. C++ will maybe take you more time to get there, but you'll have something like maybe more transparent in some way.
Which has tougher type checking?
Sorry?
Type checking. Who is more strict? Python or
Templates.
Time checking.
T by T. Type.
Type.
T by T. Type checking.
Type checking.
Type checking.
Usually type language and is strongly done.
Yeah, so Python is not, there's no type checking in Python, right?
Incorrectly written C++ code, there also you can release this type checking.
Yeah, if you do a template with a dynamic vector or something like that. But yeah, it becomes quickly like these addition, this wrapper to make how do you call it again? Like these dynamic pointers, you know. I always found that like these templates kind of add a lot of clutter to the code. Yeah.
Thank you.
So we have a couple of questions from the online audience. I start with our colleague, Dr. Sirastapa. So he's asking if you have any comments about unit testing and team-based code development. Does Python provide any advantages?
Probably it doesn't provide advantages over a language like C++. I think it provides as many tools as you would have in C++, for example. If you compare to Matlab, I think these DevOps components have been much less well developed and used in Matlab community. So I'd say that Python has a big edge over Matlab, but it's comparable to language like C++, for example.
Mm-hmm. And there's one other question. It's a specific question about a Python problem, but I can paraphrase it. So it's like about the manipulations on the strings, exchanging characters, these types of applications. And is there any way to get these types of manipulations on the GPU instead of CPU using Python?
I have no idea. I don't do a lot of GPU programming, to be frank. Normally, I don't have to optimize that much my code because most of my code will take like 1 second or something like that to run. If it takes like second to worst scenario will be that it may take like 1 or 2 hours. I'll start it when I go to sleep and I'll have the result in the morning. And the worst case is that I have to run something that takes like 2 hours over 400 recordings. Then I'll create a script that process 1 recording and I'll run it on the cluster through Slurm. So I'll have 400 jobs that take 1 hour or 2 hours each, and I'll get my output. So probably that I suppose that this question comes probably from someone who do AI application, deep learning, stuff like that you want to run on GPU.
I think I was specifically asking about string manipulations, working with characters, which I don't think we have like a GPU package. I'm not sure on Python, like for TensorFlow or something like this.
So you have CUDA, which is a GPU which gives you ability to run software on GPUs, but I don't know what are. So as I said, I didn't use it. I use it sometime through Keras, for example, and for machine learning application.
They don't have a native way of using CUDA in Python yet. They're working on it. There's like one in preview or beta that NVIDIA is working on, but I don't think it's like released yet.
Yeah. Yeah, so unfortunately, I cannot comment a lot. I don't have much experience with the GPU programming.
Yeah, I also had the question, but we can talk about it offline. I believe we've already 10 minutes over. So thank you very much again. Very